Good afternoon and welcome. Wow, thanks for being here. This is the third annual Lawler lecture. So we're welcoming everyone back who's been here before. How many here have been to a previous Lawler lecture? Awesome, thanks for coming back. And thanks to everybody who's here for the first time. Hopefully you'll be here for many, many more, because the purpose of this lecture is really to help us build community. And it's a great opportunity for all of us to get together and have a chance to listen to an awesome lecture, talk about old times, talk about new times, and catch up with how everyone's doing. So thanks for being here. Today, in a minute or two, I'm going to let Des take over, and he's going to introduce our speaker today, John Tobiason. Just so happens that John and Des both graduated from the University of North Carolina, as did Jerry Spitell, and Des and John were actually in school together, starting graduate school a few years ago. But I was actually at UNC yesterday and had the opportunity to talk with a bunch of people, and one of the things I was tasked with doing is to say hello to Des, John, and Jerry from like a few people. And so I don't want to hold everyone up today while I go through this entire list of people who were so excited that Des and John were back together here, not so much at UNC, but at UT. And we're really excited to have John here to celebrate our program, celebrate the Lawler lecture, and celebrate all of you. So with that, I'm going to turn it over to Des for the introductions of John.
So I'm going to take a few minutes and do a little bit more than just introduce John. We'll get to that in a minute. But first, I want to say thanks so much for coming. I'm wondering who's here. Who are working professionals in town who are here today? Let's see a show of hands. All right, awesome. All right, we've got a lot of emails out. Thank you so much. How many EWRE grads are here in the audience? Oh, awesome, great, thank you so much. And how many current UT students do we have in the room? Also awesome, super. Thanks very much for coming, everybody. It's really cool. For the last several minutes you've seen, I just turned it off, but the list of donors to the so-called Desmond and Alice Lawler Endowed Excellence Fund in Environmental and Water Resources Engineering. Phew, what a title. So Alice and I are very grateful to all of you who have given to that fund, which allows this lecture and a few other things to happen. So thank you so much, both for the corporate donors and the individual donors. I'm going to take a little aside here. I think probably almost everybody in the room knows that after many years of trying, I eventually published a textbook with Mark Benjamin. And this is my own personal copy, and it has, I call it my yearbook copy of my book. And anybody who ever took my Phys Chem graduate class, I want you to write me a note anywhere you want in here, and there are already a couple hundred in here. So if you haven't done it, it'll be on with the cookies, etc., after the lecture, and I'd love for you to write a note in there. All right, now to John. It was the fall of 1977. I was starting my fourth year as a PhD student at UNC, and in the door walks John Tobiason, and we became kind of instant friends, pushed together by Charlie O'Melia, who was our mutual advisor. I actually had both Phil Singer and Charlie O'Melia as my advisors because I was so bad I needed to. But anyway, so I got to know John right away, and his wife Leslie, who's here, Leslie Johnson, here in the audience. And I should have also, next to her is my wife Alice, who's also here. So anyway, Charlie O'Melia had this harebrained idea about that time that we should be able to model how particle-sized distributions change in a water treatment plant. And he gave a seminar about how that should be possible, having, of course, no idea himself how to do it. And I took the bait and said, I want to do that. And so Charlie said, okay, you can do that. And he wrote an abstract to an ACS symposium on particles in water that we would have this working model. Well, it was a harrowing experience. I'll just tell you without the details that the morning, my talk was like at 9 o'clock. And at 8:10 in the morning, I put the last dot on a hand-done overhead slide, which of course, this is long before PowerPoints and all that stuff existed. Anyway, we got it done. I did the flocculation and sedimentation part, and John did the filtration part. So there we go. And that ultimately resulted in a publication that is in this book called Particulates in Water, Characterization, Fate, Effects, and Removal. And the last chapter in the book is Integral Water Treatment Plant Design from Particle Size to Plant Performance, with authors Desmond F. Lawler, Charles R. O'Melia, and John E. Tobiason. There it is. This happens to be the first refereed publication on both my and John's resumes. So anyway, that's how I got started with John. Since then, John's and my professional careers have been intertwined, starting with that experience. We were on AWWA committees together. He's given lectures here before. I've given lectures at UMass before. We've done a lot of things together. And I guess it kind of culminated with he and I and our colleagues here and his colleagues at UMass put together a proposal to EPA for a pretty large project that we won. We called it WINSS, WINSSS. And it was this, it stood for Water Innovation Network for Sustainable Small Systems. And I had to look it up this morning, to be honest. So anyway, we've been friends and colleagues from far distance for all these years. So John finished his master's in 1979, went out to work for a consulting firm in New England for about 6 years, which turns out to have influenced his career as an academic as well. Then went back to get a PhD also under Charlie O'Melia, but Charlie had moved to Johns Hopkins University at that time. And so John did his PhD there under Charlie's direction and graduated in 1987. And since then has been a faculty member at UMass Amherst and rose through the ranks and recently was the department head there for the last 5 years, I guess. So among the many things that we share, John has a whole litany of awards that I won't bore you with reading. I just want to point out that he and I both have won the Charles R. O'Melia Distinguished Educator Award from the Association of Environmental Engineering and Science Professors. And I know it's as meaningful to John as it is to me to win an award that carries our advisor's name, so it's pretty cool. So, Distinguished Educator, John Tobiason, is here. Thank you.
Okay. First task is always to load the presentations. So there's a desktop that I'm looking at, and I'm going to guess if I double click on that, it's a go. What do you think?
On this.
Yeah. This one? No.
The red one. That
Oh, okay.
That's it.
That one?
Yep.
Okay.
Nope,
No.
wrong one.
Yeah, I was going to pick the one that I chose the name for. Okay. No, how do we get rid of that? How do I get rid of that? Somebody help me out here.
She's coming.
All right. Can we get rid of that one?
Get rid of this one?
Just, yeah.
Get rid of that.
Yeah, just, there it is. That's the one. Thank you very much. All right. And then I need that to presenter mode.
Oh my goodness. Try this one. There we go. Presenter view. Boom.
Perfect. Okay. Right subject, right place, time. We're good. We're good. Although the risk is low. Yeah. Is it on now? No? On? Not on.
They turn it on. They're controlling it up there.
On. Okay. All right. So that means I can be silenced. That's good. Done. Thank you, Lynn. Thank you, Des. Thank you, University of Texas Austin Department of Civil Environmental Engineering, Environmental and Water Resources Engineering program for this amazing honor of being invited to give this lecture. It's very humbling to get this opportunity. And I've had a great day talking with people, and I'm going to retell a little bit some things you heard, but with some embellishments just a moment ago. Let's see if I can work the slide advance, and not shut everything down at the same time. So we'll see. All right, here's what I plan to get through. It's going to be a little fast and furious because I struggled for 2 days to cut things out, but didn't succeed. So we'll see how we do. So a bit about my path, working with utilities, some things about one technical subject, disinfection byproducts, some things about another technical subject, manganese, and some things to tie those things together. So, as Des mentioned, I showed up at UNC Chapel Hill. I had done a bachelor's degree in civil engineering with environmental option. I always was interested in environmental things. And this ties in. I spent the summer of '77 out west bagging volcanoes, including Mount St. Helens before she blew. And went out to Chapel Hill, and first, actually, also was mentored by Phil Singer. First thing I got paid to do was do some water chemistry modeling, and worked with Charlie. And started doing media filtration, and I haven't stopped since. We'll get to that. So I met, and I share a lab with this guy. And believe it or not, a picture in between the wall with my filters and the bench are 2 desks facing each other. We're in between those 2 things in the basement of Rosenau Hall at UNC Chapel Hill. And so it continued. I had the great fortune to marry Leslie Johnson in the summer of '78. And thank you for being here today. And continue our friendship with Des and Alice and little Katie Lawler. I'm going to be 2, is what she said at the time. And then your first Lawler lecture arrived at UNC Chapel Hill in August of '78. And this is a picture of Dave making some DBPs, which he's never stopped doing either. And also, Jerry Spitell arrived at that same time to do his master's degree at UNC Chapel Hill. We played a little basketball, had some fun. He was a good basketball player, and Des too, not me. But I had to graduate, work with Charlie, and headed out Leslie and I, for about a half a year in that truck. And we headed out once, had some stability problems, left some things back with Des and Alice, and had to retrieve them later. And then your Desmond Lawler headed to UT Austin on January of 1980. So I worked in consulting for 4 years and got my PE. And then I did want to get a shot at this job, so I got my PhD by returning to Johns Hopkins University with Leslie and our 1-year-old son, Anders, and started that at Johns Hopkins. And I had an incredible experience. I believe Jeannie was doing work here at UT at the time. I remember talking with her from lab to lab over the phone. It's this fixed device on a wall, black usually. During the middle of that, this kid came from Israel named Meni Elimelech. Your second Lawler lecture showed up at Hopkins, and I showed him how to run filter media experiments in the basement of a building there, and he's done pretty well for himself. So Meni's amazing, and I started my UMass assistant professor job doing, yet again, media filtration experiments. And a week and a half ago, my last PhD student defended using those columns in the other picture, so I never got away. But I'm not here to talk about media filtration, am I? I'm here to talk about these subjects. So why? Well, good fortune. I went to UMass Amherst, and Jim Edswald and Dave Recco, who actually know something about DBPs, were there, and I learned a lot from them. And of course, I had a basis in it with going to UNC and Phil Singer and stuff. And then during my first year, Bill Nockey from Virginia Tech was on sabbatical, and we started doing manganese and haven't stopped together. So those things happened. And really, the subjects are pervasive, complicated water quality challenges for utilities. So that's really the reason that they're here. Fun, complicated, but super relevant to day-to-day operation of every drinking water treatment plant that meets regulations in this country every day. So we have to pay attention to them. So the question, this comes out of, Dave and I had a chance to present a lecture and talk about our lot of work with utilities and agencies. So why do that work? Why work not for NSF or NIH or something that, and I think there's questions to be answered by PWSs, public water systems, that retain usually the regulations, but sometimes not. They don't have the staff time or the ability or the facilities to undertake the work, and they value their role in workforce development of students. They value their role in that, and that's critical to the teaming. The university values that student experiential learning. Now we call it experiential learning experiences, and the scholarly output. And also, there's a role of a public university and my responsibility as an engineer, scientist, and educator to engage with those people. So this community of working with them. The scope of things we've done, you can look through and catch some of these words. A lot with natural organic matter, a lot related to removing particles, some destroying trace things. We were just talking about oil. I forgot to mention we modeled and then boldly tried to do some experiments in the lab with spilling oil in a reservoir and seeing what the Massachusetts Water Resources Authority could do with very few processes, what that would do. And what could we get? Dave came up with some West Texas crude, sweet, that's what we could get our hands on to bring to the lab to do something with. And then also starting from the source, done a lot of work in watersheds and reservoirs, water quality modeling. And then on the other end, into changes in water quality from the treatment plant to the consumer. And most recently and currently, Mary Jo, your own Dr. Kirsitz runs a project, EPA funded, that we work on related to disinfection byproducts and pathogens in drinking water systems. The UMass folks are focusing on DBPs. So a couple of weeks ago, I was at one of our utilities and shipped some samples here to the lab for analysis by this project, for example. How does this work? Well, you got to have people in the utility or at an agency that understand the need to learn from the research, they ask good questions, and they value workforce education. You've got to have faculty who appreciate that interaction and see where this stakeholder-based work really benefits their career interests, if it's good in their students' best interests. You need some patience and time to interact. You need flexibility. Sometimes the utility needs something that wasn't your fundamental thing done, and you need to be responsive to that. And you need to collaborate between everybody. So all the things that the hallmark of good community-based work in general, and I think you have all these things here at your EWRE program here at Texas is amazing. It's been great. By the way, our program is also called EWRE in our department. By that name, we've had all that together. All right. So that's some background, interesting. I got to get technical for the rest of this. So the first one is about disinfection byproducts, and although it's an extremely technical audience, which is great, based on raising hands, unless you happen to be the HR person from the local firm, but probably not, you're here. So, right, we do disinfection. What I mean by that is applying things to water. The water's got constituents in it in addition to water, and it yields some things that we call disinfection byproducts, the byproducts of the disinfection process. And it's really important. The disinfection part is a critical step in our barrier to protect public health, right? It's a treatment technique we use to protect people from maybe the occurrence of pathogens, maybe not, but we have it in place. On the other hand, the disinfection byproducts, unfortunately, we have health concerns that are more in the toxicity and chronic level as opposed to acute. So we have this challenge of something we have to do, but something that creates problems we're worried about. So just some definitions, and I'm going to apologize. Some of the slides I'm using here are very much teaching slides, and so they're a little deeper than they need to be. So primary disinfection, what we mean is we apply a certain level of disinfection that's regulated, that every utility in the United States every day has to report that they meet this regulation, every day. It's a necessity of doing the job of providing water. So we might do it in the beginning, we might do it in the middle, we might do it at the end of treatment processes, and the disinfectants that we're allowed to use by regulation to meet this goal are listed here: free chlorine, chlorine dioxide, ozone, UV light. And chloramines are allowed, but very rarely do we have the time required to provide primary disinfection by chloramines. The occasional 10-mile pipeline between A and B, yeah, but most cases we can't do that. All right, whoops, there we go, I did it. Okay, secondary, that's the provision of a residual in the distribution system to continue to protect water quality, maybe provide some biostability, protect against recontamination, and indicator of water quality. It's kind of, some of the aspects of this are tied to this co-down project of whether this is here or not. Not everybody in the world believes in this or requires this practice, but in the United States, we do. And this usually, though, is only free or combined chlorine, or chloramines, not an occasional short-term chlorine dioxide. So we have this paradigm here where we start with a requirement, we go out to here, and I put may change there because I know Mary Jo's involved with the committee and the government. We are revisiting our disinfection rules and surface water treatment rule, and we may change that to not just detecting it or sniffing it, but to actually measure a number there. For example, that's one of the things that might happen. And we've got homes and buildings and storage tanks involved. So what's regulated? There's a bunch of organics regulated, the trihalmethanes and the haloacetic acid. So the bold part there, we have a number. The LRAA is a locational running annual average. We have to take samples from a distribution system, take the average over the course of a year, and be below this value. On the bottom there, I want to point out that if you actually look at the compounds being regulated and their associated toxicity and health risks, and our knowledge of some increased types of health problems, maybe bladder cancer related to drinking chlorinated water, these are not the compounds causing that. These are not the things. So they're really a surrogate. They're really abundant compounds that we can measure and offer control of. And the notion is that if we control these compounds well, we'll also control other things that we don't know as of yet are the cause of those concerns. So it's important to point out, and particularly brominated compounds. We mentioned brominated compound today, Pavel and I think, in there. So some inorganics are bromate and chlorite. You'll see where that comes in a minute. And also, we don't like to call the things we do to protect public health contaminants, so we came up with another word called maximum residual disinfectant level, otherwise known as a maximum contaminant level for the things we apply to help us out, right? So it's a two-edged sword. Good, bad. We got both things going on. All right, so how do we control DBPs? And really, these are the three main messages, and then I got a lot of flavors of how we do it. But we can control our choice of the processes we use to achieve the objective and perhaps minimize the occurrence. We'll talk about that. We can control or manage the precursors, the things that the disinfectants react with in the water. And lastly, and I'm not going to say any more words about this, one more word, remove or destroy the undesired DBPs. The least good way to go to do this would be better to not make them in the first place. So, some color coding here. Green, if you're not colorblind, this is going to be good. Green is good. Brown means that this aspect also ties to manganese. So the brown is that thing I'm saying there ties to manganese. The green is that it's good. So free chlorine is great. It makes, unfortunately, it makes regulated trimethanes and haloacetic acids. The pH is a big player in disinfection. It also is a player in the control of manganese. Natural organic matter, the nature of it, the amount of it is a big player, and it reacts with all the oxidants. Oxidants are also reacting with manganese, so it's another thing that interacts. And it provides a residual for secondary disinfection. Green is good that we have that residual because we have to have one. Unfortunately, and while it's providing that residual, the continued opportunity to make DBPs as that residual exists and we go along in the distribution system, and by the way, to oxidize manganese when we don't want it to be oxidized. So these things go hand in hand. Ozone, you may have heard more about this from your first Lawler lecture, Dave. This is one of his favorite topics, ozone, but it doesn't make much THMs or HAAs. It's a very effective disinfectant. But it does make bromate, and there's no residual for secondary disinfection. Chlorine dioxide is another chemical that doesn't make many DBPs. It's effective disinfectant. It yields a DBP chloride, and it turns out the yielding of that limits the amount of chlorine dioxide we can provide. So if our goal is to treat manganese with that, we may not be able to add enough to achieve our objective because the byproduct's regulated. Little catch-22. That's that combination part. It also doesn't do much for your residual. UV light, I just mentioned, it doesn't make THMs and HAAs. Good thing. It's really effective, especially for protozoans. Good thing. It doesn't provide any residual, and of course, it needs to get to the pathogen and not bounce off some other particle before it gets to the pathogen, right? So you got to have the right water. So what about the secondary disinfectants? You're going to use free chlorine. You're going to keep making DBPs. So I mentioned that slow oxidation, and it's good to limit the time and to decrease formation. Chloramines, Jerry's favorite subject, is one of his anyway, is also good, and we do it a lot to meet regulations in this country. A lot, like 40% of treated drinking water, 35%, some number in the country of treated water. It doesn't make THMs and HAs, but it might form some unregulated compounds of concern. It could be nitrified and be destroyed in the distribution system. But maybe it's better to control biofilms, which may be impacted opportunistic pathogens, than free chlorine. So a bunch of things going on there. A little caveat here in the drinking water world, I think most folks are aware of this, that you got to beware in making a conversion from free chlorine to chloramines because you might have unintended consequences with lead in Washington, D.C., for example, and also a lot of places end up with what's called a free chlorine burn, which is great for operationally, and no one talks about the water quality produced during that burn because nobody wants to know. Nobody samples for regulations during that burn. It is not a place you want to be. So it's not a great thing. Unintended consequences. All right. So a little bit on the science. So this is a Dave Reckow slide that I love. So the precursors, free chlorine. Whoa, let's get back here. Free chlorine, NOM, and bromide. I'm not going to say much about this, but it just turns out that bromide reacts super fast with free chlorine, makes hyperbromous acid, and hyperbromous acid reacts really fast with NOM compared to free chlorine. So you don't really like that to happen. So fortunately, to make a problem usually requires a fairly high level of bromide. It depends where you live and are, whether that's a player or not. So you make things here, and you make chlorinated organics. We track this stuff, and it happens over time. This is time, and maybe the water had some to begin with, and you made a measurement of it. There's chlorine, and it forms over time. And it's this track over time that has to do with the distribution system, contact time in a treatment plant. How can we control that? And one of the ways to control that is come along here at some level that's okay and throw ammonia in to make chloramines and stop it. That's one way. And that's really why that's commonly done that. But there are a couple things. Formation potential is, imagine we've got something that could make something, but it requires this other ingredient, and we add 10 times as much of that other ingredient as possible to use up all of the one thing, and that's called the potential to make something, okay? It doesn't happen in reality. This is a slide from Dave's PhD with Phil that I just want to point out. pH, here's pH. Two regulated things, HAs and THMs. Should the pH go up or down? Depends, right? That makes more THMs and less haloacetic acids. So it's not a simple answer, right? It's complicated. It's mixed with those two things that happen in here. We get multiple effects. Notice in the lab, you study things down to pH 2 and up to pH 12. Notice in drinking water treatment, we only deliver things between here and here, right? That's all. We stick in there. But in the lab, you need to understand those things. Okay, so the management of precursors. The biggest thing we learned at first was don't chlorinate raw water. Don't add chlorine to the maximum precursor level. So that changed a lot. Maximize the removal, all right? Most commonly it's for NOM, not bromide. But the problem is if you do that, you increase the ratio of bromide to NOM when it does occur, and you can make more brominated DBPs, which is probably the toxic DBPs. And by the way, it's a mass-based health standard. Bromide is a lot heavier than chloride, so it turns out for the same number of moles of stuff, you get a lot more massive stuff, and you violate the regulation just because they were brominated, not chlorinated. So it's a couple of classic cases that happened. So the other thing that I'd probably spend more time on in studies with utilities is practicing optimal coagulation, maximize NOM removal. But sometimes the optimal pH for coagulation can be at odds with great manganese oxidation. So that's a problem we have to face. And then we study all kinds of ways to do additional NOM removal, and I'll only mention a couple of those things. So there's ways to do that. And we have this fortunate thing that things we measure in the water about organic carbon also correlate then when we chlorinate it with trihalomethane formation potential. This is one particular set of data for TOC. And then it turns out something that's really easy to measure in the lab, UV absorbance, super cheap, super fast, also correlates with TOC, and it's great for controlling coagulant dose. So ergo, oh yeah, the slope of this is specific UV absorbance. Don't have time to talk about that, but it's the character of the organic matter. UV and THMs correlate. So we can use a simple measure of UV and get a good idea of how treatment performance works. So we'll do that a lot. Classic jar test, UV is a function of dosing of some coagulants and optimize to get a very low level of UV. This is the classic way to control NOM and get good performance. Another way to do it, and this might have been measured by Dan Wilson, maybe. I'm not sure. Overlaps, Dan. We'll see. Let's see. I can't remember if you did this or Amy did this, but one of you did. This is a breakthrough curve for carbon contactor. So imagine you're going to use a carbon contactor, GAC, to remove organic matter. And this is, this is DOC, UV, and THMs, and you see it correlate. So Dan may have done the membrane studies that were parallel to this, but I don't remember. Or both. I know he made the membrane system work. I remember, oh man, I'm sorry. Well, I know he made it work. Okay, so the other two choices, or a couple other, are let's destroy the DBP precursors. Just make them not make DBPs. And so we can add oxidants to do that. And the cool thing about doing that is we also do that for manganese control strategy. So maybe we can get both out of that. And we might find an additional decrease, but sometimes we can get it all by coagulation anyway. Sometimes. Sometimes it's a decrease. And then something that some of you in here have worked on as well, we might be able to remove more DOC if we allow part of the process to be biologically active and biodegrade the DOC. So it's another removal mechanism to get rid of precursors. Okay. And just because it's recent, from that same PhD student I mentioned who was doing filtration, it was full-scale work. This is chlorine dioxide on and off at a plant called the Putnam Water Treatment Plant Aquarium. So it was off, and then every summer they turn it on. And then a little bit later, we turned it off for a couple of days just to see this impact. So we went off to on and on to off. And in all these DBPs, basically 5 to 15% decrease in DBPs resulted with the pre-chlorine dioxide on. So a win for that. She was not studying that. She was studying its impact on filter performance, which I'm not talking about today. But anyway, that's another topic. Okay, so the summaries are multiple strategies, managing the disinfectant, maximizing precursor removal, possible DBP, only generally works for making an air quality problem, THM stripping, perhaps, and along the way, we can't compromise disinfection. You know, that's a cardinal place to be at. And it's got to be integrated with all our other treatment objectives, by the way, one of which is manganese control. So let's switch to that topic. So the second technical topic is manganese. And I have this, these are some preaching points at the beginning, which is, one is, in the water profession, you talk to somebody, yeah, we do iron and manganese control. We treat that for iron and manganese. And it turns out that there are two things. One is iron, one is manganese. They're very different. Sometimes they occur together, sometimes they don't, but it's not a word, so just got to pay attention to it. It's a very common need. Complexities are often ignored, myths perpetuated, and mistakes made. And now, and I'll talk about lack of characterizations of forms, and with our super accelerating attention to PFAS, turns out a lot of groundwaters that contaminated with PFAS also turn out to have a lot of iron and manganese. And if you don't pay attention to that, you can plan the greatest PFAS removal system in the world and have it not work because of iron and manganese. So it's this pervasive problem you have to pay attention to. All right, I'm going to, Jez, how am I doing? Okay, all right, so why do we care about this one? I mentioned DBPs, largely aesthetic. So DBPs, we don't see them, right? There's nothing, you're never gonna pick up a glass of water and go, geez, the THMs are brutal in there, right? But if you pick up a glass of water and it's cloudy and brown, geez, I don't wanna drink that. Even if it's only precipitated ferric hydroxide, it's probably good for you. So really, people go out of their way to put colloids and things in water to drink. So anyway, it's largely aesthetic. We don't like sinks. We really don't like stained laundry. And we have some what we call secondary aesthetic limits. They're not good enough. They're outdated. They should be better. And it's really easy to meet this goal for manganese and this goal for iron. Iron's mentioned. I'm going to focus on manganese, but iron's mentioned. So we have a lifetime health advisory. So there is increasing levels of concern of manganese from a health perspective. And the most recent study of that, to reach a conclusion, was Health Canada in May of 19 set a 0.12 milligram per liter level on a health basis. And so that's a lot lower than 0.3. And the World Health Organization provided a provisional health-based guideline, I guess that's more recent, of 0.8, so 80 micrograms per liter. And Health Canada put the aesthetics at 0.02, and for iron, we don't have those. So a lot of interest. It is on, manganese was on the unregulated contaminant monitoring rule, UCMR4, so we have a lot of data on manganese occurrence in the country. Big hot spot in New England, where I happen, in the Northeast, so we happen to pay a lot of attention to it. All right, so that's why we care about it. I also mentioned this. So Lynn would appreciate, of course, to know this. Well, when you make iron or manganese particles, they tend to like to other things associated with them. So they might just be a carrier of some other toxic trace level component that you didn't plan on. So that's another reason to pay attention. So where does it come from? In groundwater, it's often fairly stable over time. This is a picture of a well near our house in South Amherst, Massachusetts. There's iron or manganese or both. Usually they're the result of really reducing conditions and often associated with microbes who just want to dump electrons on the enormous abundance of iron and manganese oxides in the Earth's crust. And if it's a place to go, we get reduced iron and manganese. And it's relatively stable, and we have some co-contaminants. This picture's here. It's not an iron talk, but in my opinion, it is impossible to bring a sample from a groundwater with reduced iron to the lab and not have it change. I've worked very hard to keep oxygen out of that sample, but it fails. Nitrogen, baths, all kinds of things. So this is doing the work at the place the water comes out of the pipe. Because it turns out the water stays in the pipe and goes to the consumer. It doesn't get a chance to go to the lab and change. So you have to figure it out. All right. Surface waters, it's usually seasonal, usually for anoxic conditions that allow microbes to reduce manganese. We get significant seasonal variations. Usually in river sources, manganese is particles. In treatment plants, sadly, when we remove it, we can also recycle it because we put it in sludges and it comes back around in recycles. That's a problem. And darned if one of the coagulants we often use in the business used to be worse, it's not as bad, iron chloride is contaminated with manganese in the production process. So if you're the Metropolitan Water District of Southern California, you didn't know you were dosing manganese to your water for 30 years and coating your filter media with manganese oxide until you decided to change a process that made that a huge problem, right? And millions of dollars to replace filter media. So we can have release, and we can have other things going on. All right, so there's three control approaches. Minimizing the source water. Can do some things with groundwater, blend sources, surface water, reservoir aeration, understanding that, using multiple intake depths. Treatment, we're going to talk about that. And the last one I mentioned, because it really should be a big red X through it, and let's not do this anymore, because we've been pretending too long this is useful. So sequestering. It's the notion that we can add something to the water to interact with these reduced manganese and iron and prevent it from being oxidized where we don't want it to be oxidized. We had one student study this effectively. Iron, never, not a chance. In the presence of free chlorine, by the way. That's out in the distribution system. Iron, not a chance. You stabilize colloids of iron, but never reduced iron. Manganese, semi-effective. All you have to do is go out to a system that does this and open a fire hydrant, and you'll see where the iron and manganese are. The distribution system is a very effective removal system, and unfortunately, it's all, I have a great slide, it's just black pouring out of a fire hydrant, and we went out and made measurements, leaving the plant at the people's homes. There's only 20% left. Where was it? It's in the pipe. So it's a problem with all kinds of other co-constituents. So it's in there, all right? So I'm not going to do questions while I'm rolling along, all right? So there's a lot of forms. For manganese, I'm going to focus on, that's the reduced form. Permanganate is something we make. So here's a weird one. We use manganese to treat manganese. Not the best choice, but anyway, we do it. Manganese makes a lot of solid forms. various oxides. So a lot of times we write MnOx because the X might be 2, it might be 1, it might be 1.5. So we just work that out. And so occasionally we make manganese carbonate here in Texas where you have some hard waters and you might precipitate manganese carbonate. I believe Des has looked at this. And at very high pH, you might be able to oxidize manganese as well. All right. So there's another little thing working in this. It turns out that you really need to know whether the manganese or the iron is or isn't oxidized before you apply a treatment technique. And the challenge is that sometimes it's oxidized to very small, stable particles that if you don't do the right separation technique, you think they're dissolved, and you apply an oxidant to oxidize already oxidized things, it doesn't go well. Right? Bad things happen. So we do a separation to make particles, colloids between about a couple nanometers and a few nanometers and 0.2 microns, and then we call this dissolved. But you can pick any one of the numbers you want in here, and there's a continuum, a spectrum of stuff. So we do this, remember, there's nothing dissolved that isn't operationally defined as dissolved, that we measure. They exist that way. All right, so any of you students in the lab, right, so some syringe filtering, an ultrafilter. So here's the problem with this. See this apparatus and see that red tube? That goes to a nitrogen tank to provide pressure. This is a pain to do. No commercial lab does this. A few utilities and a few things. And it's important to know that difference between colloidal and particle. So what do? There's one easy solution. You take a sample and you aggregate it, coagulate it, and you do that before and after a simple separation step, and the difference is the colloidal, because you make them big enough to be removed by the... But that's not, like, easy to do either, so it's important to do this. All right, removing manganese. The super simple thing is become a particle or get to a surface. Those are the two things. The stuff becomes a particle, and we take it out through all our particle removal mechanisms, or we get to a surface, and things happen at surfaces of different sorts, many different surfaces, and we get it out. Those are the two simple things. We wrote a paper a few years back about summarizing this. It starts here. If it's a particle or a colloid already, go this way, take out particles. If it's not, make it a particle and take it out, or get it to a surface. Some of those surfaces make particles, and they come out over here. Some of them don't, and it goes out in a waste brine. So that's the basic thing. Become a particle directly or get to a surface, right? Or be a particle to start. But usually we're not here. That's a problem, it's over here. Okay, so in terms of chemical oxidation and particle removal, we do it by adding oxidants, give some time, do some kind of filtration, and we take the particles out. If it's a surface water, usually it's a part of other processes, coagulation, flocculation, some kind of clarification, and some kind of separation. So we do that. In the teaching of a physicochemical process course, we talk about chemical reactor engineering. There's really two key steps. I call them how much and how fast. The fancy words are stoichiometry and kinetics. So stoichiometry, add the right amount of oxidants, also operating costs. If you're going to go to the engineering, this is operating costs. So we're not going to talk much about manganese. It turns out there's this interesting thing that manganese and iron have about the same atomic weight, but manganese gets oxidized with a 2-electron transfer, and iron only 1. So you need twice as much mass per mass of iron versus twice as much per mass of manganese as iron of the oxidant you're adding, right? You got competing oxidant demands, other reactive species, so you've got to add in excess of the stoichiometric amount, and it varies with everything going on. Proper dosing in this approach is challenging, especially in a surface water that changes a lot. Did one study where the diurnal, during the day variation in dissolved manganese entering the plant was amazing. Trying to track that with permanganate dosing, good luck. It's really difficult to do. And Lynn would appreciate this. I think the creation of particles may result in unexpected dosing. Particles are reactive surfaces, particularly small particles, really reactive surfaces, so surprising things can happen. In many cases, it's beneficial. Turns out we can add less than we thought we had to because of catalytic oxidation on the surface. And then reaction kinetics, how fast it's going to happen. this is capital costs for the engineers, right? How big a tank you got to build? What's the mean hydraulic retention time? What's the hydraulic retention time distribution? So how much time do we need? And it's a factor of a lot of things: water quality, competing demands. And a cool thing with iron and manganese I just have to mention is that you can oxidize iron with free chlorine and not make any DBPs if you just add enough to oxidize the iron, because as you may get taught in chemical reaction classes, when you have multiple competing reactions in parallel, the fastest wins. The fastest wins. So in this case, the iron wins, and the free chlorine in the NOM, they don't make DBPs very fast. Iron wins, and we can use free chlorine, use it all up, and just do that. It's kind of cool. And we can do batch testing to get to that. Just want to say something about the particular strong oxidants here. We can make a lot of stable negatively charged particles with strong oxidants, and if you do that after coagulation, they are stable small particles that media filters don't do well with, okay, because they're stable, not because they're small. And it turns out you can overdose. Turns out permanganate, if any of you done it, is this brilliant pink, purple color. But most people don't like purple color in their water. So if you have permanganate, that's a problem. So permanganate itself can do it. Ozone can oxidize all the way to permanganate. Ferrate can oxidize all the way to permanganate. So you got to watch out. Also, they make DBPs, bromate and chlorine dioxide, so have their problems. And it turns out with ozone, it's really hard to get very low levels of manganese. And then if you add an iron or a manganese chemical to deal with iron or manganese, you're just making more iron and manganese residuals to deal with. You're just creating more problems. So it's long been used, but it's not the best. And then sometimes the oxidant can give you other benefits. Harking back to our first subject, you can get disinfection out of ozone and chlorine dioxide, and maybe do some taste and odor destruction or cyanotoxin destruction. So those are good things. Permanganate gets no disinfection chops, unfortunately. And a few other things we do that probably give us disinfection, they don't get credit for it. Okay, so there's some graphs from work done at Colorado State. Permanganate, chlorine dioxide, and ozone. And mainly, this is starting at 60, 200, and 1,000 micrograms per liter, and showing you that chemical kinetics makes sense. It goes faster when you have more to start. The rate is higher. This is 300, this is 5 minutes, this is quite a few minutes, and this, what the main point is, it never gets down at this 10 or level, super. So ozone is hard to get low enough. This is faster than chlorine dioxide, and there's a lot of other variables in this as well. So this is my graph to tell you something I said to you in words, and I could have saved them for this. Direct filtration treatment plant, raw water, 0.065 milligrams per liter of manganese coming in. This is rapid mix with no pre-oxidant. The dissolved manganese goes right through. And if you have a filter with no pre-oxidant, it goes right through. So manganese just passes through the system, right? If we pre-ozonate and then run it through rapid mix, these colloids, which is the dashed area, and the dark is particles, get aggregated into more particles and they're removed by the filter. The plant itself, this is the full-scale treatment plant, used permanganate, it makes colloids, and the total amount of manganese goes up. Remember that part? So the manganese is a lot more. We do rapid mixing. We got a lot of particles, and they're all removed well. So it turns out if I went out in the field and I measured dissolved as being less than 0.22 microns and particulate here, I would have seen this result and said, oh my God, there's no oxidation of all that manganese. I better add more oxidant. Completely the wrong thing to do, right? Completely wrong. It's already colloids. It's just not particles. So you can make that mistake. A laundry on Cape Cod in Hyannis, right next to a fancy hotel, when it opened and moved in the system, had spent a lot of money on treatment facilities that failed because of colloidal iron staining the white laundry for this fancy hotel on July 4th week. And it was because he'd bought media filter and ion exchange, neither of which touch colloidally stable iron, neither of which. So didn't get very good advice. But we figured it out. Okay, a little myth, or just to comment on about manganese and weak oxidants. And so I call chlorine a weak oxidant here. And the reason is that there's somewhat of a myth, and it's usually in most textbooks listed this way, that we add free chlorine at the pH of most drinking water plants, most, 6, 7, maybe up to 8, free chlorine and manganese does not oxidize manganese in solution in the time scale of most treatment plants. We don't spend a day in the treatment plant, right? We spend hours or a few hours. So it doesn't oxidize it. If you run the pH up to 9 or 10, yeah, it'll oxidize it. It will do that. But it turns out free chlorine is essential for one of the methods of removing manganese, and that's sorption and surface catalyzed oxidation. You put the manganese on a surface, and it oxidizes in seconds or milliseconds instead of days. So we make use of that, but it is critical. So if you don't, going back to my characterization, if you don't characterize things, usually we don't know how removal occurs. Everybody measures in and out, and so people think that they're precipitating manganese, but they're not. It's just not measured very much. Another thing is oxygen. Wouldn't it be great if oxygen would do this same surface catalyzed reaction? Because most water going across filters has oxygen in it, but it doesn't. It's too slow. The pH is too high. Thermodynamically, it should do it, but it's too slow. But if I have a manganese oxidizing biofilm, we know that pretty high levels of DO seem to make that work really well. So we need oxygen there quite a bit. All right, so removal by media surfaces, there's 3 methods that this gets done by. I'm going to talk about this particular one. It could be biofiltration, it could be ion exchange, but I'm just going to talk about this. And it's kind of a you like it and you don't like it situation. And the like it is this. Basically, any surface, manganese 2+ and free chlorine, and if that stuff travels across that surface, it will form a manganese oxide coating. I don't care the surface. It will do it to everything. Usually things you want, maybe granule media, but a lot of things you don't want, all these other things. So the sample line at treatment plants that continuously running to a lab sink, I've observed those be phenomenal removal. But if I go to the place it's taking the sample from at the treatment plant and do my own grab sample, there's plenty of manganese there. It's just all in the sample line on the way to the thing. So you have to pay attention to that. And it's a 2-step process, sorption and surface catalysis, and the surface is regenerated. By the way, the subject of James Morgan's PhD with Werner Stumm was this. It's continuous regeneration works great with free chlorine. Intermittent regeneration can be done, and I'll mention this. This is basically an absorption breakthrough curve type of process, so it has its limits. And the 3 classes are green sand, oxide-coated media particle filtration, and the one I want to say the most about actually is this one right here, the 2nd stage contactor, okay? So I'm going to get to that. This is a picture, manganese green sand. So green sand is a word used in our business to mean things. It means a lot of different things. It turns out I don't like it, but it turns out that green sand was something we mined, glauconite, and it is green. But when we use it for manganese or iron removal, it's not green anymore. It's only because it was a natural ion exchanger, took up cations, somebody put some chlorine on it, it turned black, and they found out it was better for removing manganese. So it's called manganese green sand, but we've dropped the manganese. So it just gets called green sand, but it's not green sand anymore. And we make some manufactured called green sand plus, that's one. And it turns out plastic media, ceramic media, silica sand, those are coated with manganese, those are with the coating taken off, et cetera, et cetera. This is pyrolusite, it's 100% manganese oxide, so you can't do that, it all goes away, right? So any surface will become manganese oxide coated. So typical green sand is groundwater, continuous application of an oxidant, and then the media regeneration is either continuous or intermittent. And I want to say that a lot of utilities think they can do continuous regeneration with permanganate. They think the permanganate is getting to the top of this filter and regenerating the media. I would posit that rarely occurs because it's a dangerous place to be. Because if the manganese doesn't react, you got pink water coming out. And if it does react, you make manganese oxide colloids that why would they deposit if they're negatively charged? So in my opinion, we just never measure it here. In my opinion, people think this is happening. It's not. And one of my goals in retirement, unknown to, is to go get some of these measurements done on my own time because I want to figure it out. So intermittent regeneration works that way. Subject I spent a lot of time is, it turns out we build media filters to remove particles. If there's free chlorine and manganese around, they get coated with manganese oxide, and we've got that, and it works really well to do this. It's reliable, effective, robust, easy to operate. Go out in some plants. This is manganese coating on anthracite, 20 to 40 milligrams per gram. By the way, I didn't show you a picture of anthracite. It's black before and after. It's not very visually appealing. And then it doesn't even make it to the sand. This is a cross-section of anthracite. It's got quite a nice deposit of stuff on the surface. A lot of it's manganese. A lot of interesting things going on there. There's aluminum and iron in there, and I don't know why they're there. So if this process is so good, this is wonderful. You just measure chlorine residual coming out, and it works like a charm. What's the issue? Well, it turns out you can't use GAC media because the GAC destroys the chlorine that was maintaining the thing. So that's a no-go. The best DBP conditions are not great for this. Maybe really low pH. And we documented in an unintended result of a study that applying chlorine ahead of the media filter can cause a 10 to 50% increase in DBPs 24 hours later, and it has nothing to do with the time across the filter, because that's minutes. It has to do with continually blasting the same NOM with chlorine, and you keep peeling off these small, remember how small the molecules are. So, and we can release manganese. So, and if you want to have a biologically active filter, you're not going to continually bombard it with free chlorine, right? Not going to happen. So what's the solution? Well, the solution is the third method, which is to let's not ask particle filters to also be dissolved manganese removers. Let's separate those. Let's let the particle filter remove particles, and let's do the other one somewhere else. So we do that, and then we use a coarse media contactor, second stage contactor, to remove the manganese. And the difference is that we can run this one, biologically active, standard media filter, and this one, we can put super coarse media and run it at 10 to 30 GPM per square foot. 30 seconds of contact time, we take up the manganese. We don't need this stuff, so it's great. This is just a different master's student did. These are manganese being removed in the depth of a 40-inch column from 0.15 down to 0.01 or something like that. We did multiple disinfectants, multiple media, all this stuff to get to that. So this was an idea from Bill Nockey at Virginia Tech. He had a column, he shipped it up to us at UMass. We did some studies with it, and we did lab scale research, and we had a utility that we had this great relationship and their consultant who boldly said, let's build this full scale from our pilot stuff. So they went from the plant to the full scale, and this plant went online in July of 2013, and now there's new plants going online to do this. So a few pictures. This is the old plant, and this is a single stage. It had TOC, iron, and manganese, and it basically is a DBP factory because you had to apply enough chlorine to the beginning of this to have a residual at the end. And in my opinion, manganese reducers are just ubiquitous and brutal. If you don't actively work to stop manganese reducers, they win. They seem to be ubiquitous. Lots of organisms can do both, and they always win. So we, as a utility, some of my students, we did pilot scale studies. Aquarian and Time Bond designed a new full-scale facility, and it worked great. So what happens across this plant? These kinds of plants, they all look the same. This could be PFAS, right? Steel vessels, pipes, valves, right? They're all the same. But what happens is this. The iron gets oxidized with pre-chlorine in this case to particles, and it's done. Iron story over. Front stage, all over, all set. Turns out they've switched to pre-permanganate because operationally it turns out if you overdose the chlorine, you make DBPs. But so it's easier not to do that. Manganese is another story. Raw water manganese, dual media filter influent, dual media effluent. So if you've been operating this treatment plant for years in one stage and you're used to seeing no manganese coming out of the dual media filter, you have to take some convincing that this is okay because we built another process to take care of it. But they believed. So dual media effluent, contact or influent. So chlorine is applied right here, contact or effluent. So we just take it all up in this contactor and it works great. But the best part is the DBP levels aren't so low, and this is the comparison. This is before these are hundreds, all right? These are leaving the plant, leaving the treatment plant, not the distribution system. So this is what it used to do. Now I'm in real trouble. Oh my God, what did I hit? Presenter mode, quick. It's right there. This is black background. This is too hard. All right, look at that. That's after the plant went in service. The gaps are because they had to take the plant offline to stay in compliance with stage 1 DBPs, not even stage 2. So that went on, and we got a couple of papers about it. The cool thing is down here, the post-contactor does not make DBPs, unlike a dual media filter. It's just oxide and manganese going on. We were worried that manganese oxide would catalyze DBP formation, just like it catalyzes a lot of other things. And everything Ariane's PhD tried to do, that's Ariane. She finished last week. She finished in January. US EPA, Mass DEP. So I've produced these people who've gone to be regulators. Anyway, so the impact was that we developed a new method for coating media. You don't have to go and buy some. Just get some sand and anthracite and do a couple of steps, and you can make the media coated. I think it's an increased role, because if we want to have particle removal filters that are also biologically active, in other words, okay, you don't have to remove dissolved manganese, but we do want you to actually to biodegrade some stuff. So we'll still have you do two things, but we can do that and just put in second stage contactors. So the last few slides are about the plant that I was at for our co-down project. It was groundwater well sources. It has traditional green sand filters run on intermittent regeneration solars. It's then anion exchange for removal, and then post contact. And this is another utility consultant, in this case, C.M. Smith, University collaboration. I was just there last week. I hadn't been there since November 22. For some reason, when we drove over the river, it was 1 mile on the way here on our way to Swans Island, Maine. Leslie wasn't interested in going and seeing this treatment plant. Can't imagine why. But there's all the contactors, and it's so cool. They're so smart. Turns out to get media, to look at it, you got to open these hatches. And most of my students are used to being up on ladders. There's not enough roof to get a sampling in. These guys built this great deck. Look at that. This whole deck, these are all the contactors, and I couldn't resist taking the pictures. Karita bought Tonka, I believe that's the case. So we've got green sand filter 5, anion exchange filter 5, and much to my delight, manganese contactor 1. Because on that first plant we built, it took a lot of work to get the provider and the consultant to not call that a filter. Worked really hard to call it a manganese contactor. So to see that on a nameplate from a manufacturer is like victory. It really felt good to see that. Yeah, I mean, it's really interesting. But anyway, that's the process. So a different set, right, of meeting this combined DBP manganese challenge. Right? In this case, it's a removal system over here that's intermittent regenerated. But now, they don't care if the breakthrough is 0.07 manganese, because this thing's going to take it all. They can run this differently. But they had this very reactive NOM, and I'll show you the result of that. This is an anion exchange pilot scale. It turns out sulfate always gets taken up first. And if you're worried about sulfite to chloride ratios, so they run their 3 contactors. They're all started at different times, so it's a blend of sulfate, and they never have no sulfate water, just to be good. This is UV 254. This is, the blue dots are what comes out of that first stage green sand filter. It does not remove NOM, never was intended to, right? And then this is coming out of the anion exchange resin, and the goal for treatment was found out by doing lots of SDS DBP measurements, and this is THMs versus UV. This is what came out of the first stage contactor. This is out of anion exchange, and it turned out they wanted to get to 60 or 50, right, well below. And it turns out that meant their goal for UV was in this 0.02 kind of range, which for that NOM, I was surprised. It turned out to be nasty. It had a high specific DBP yield. In other words, for every milligram of carbon, it made a lot of THMs, more than it should have, in my opinion, but it was the groundwater. So that's the story. The disinfection, DBP, and MN, these control strategies may conflict with each other, and that's no surprise. Throw in PFAS, throw in something else. Integrated treatment plant design requires that. We started with that subject. Des mentioned our paper on particles, integral design. I think fundamental understanding is needed to achieve success. There's these myths that are perpetuated and mistakes that are made because of not just basic understanding that. and it's got to be integrated. And the other interesting thing, and one of the challenges, I've done a lot of work recently related to small systems. I have a lot of responsibility to assist the state of Massachusetts with support of small water systems, and also point of use, point of entry. And fundamental chemistry and biology does not care about scale. It's the same complexity whether you're giant or small. And complex chemistry and having the knowledge and appropriate approach to deal with that at the small scale is challenging to achieve due to the situation we have with the fact that we produce a product that we don't pay enough for, and thus we can't pay enough labor or get enough money in to provide this water, which is essential to our life. And I talked to the students about this today. It's perplexing to me that we have a lot of things. I'm willing to pay a ridiculous amount for this thing, right? Water, I should be willing to pay 10 times as much as I pay for this for water. I can't live without water. I can throw this away and be fine. So why is that? It's a weird societal problem. So anyway, one of those big pictures in our business. And I also want to end up by saying thank you to everybody for being here. In particular, I want to thank Leslie for being with me. And hopefully now I have some time. Well, I'll have more time. I formally retired, by the way, 10 days ago. And I'm a research professor. More importantly, on July 1st, I stopped being the friggin' department head. Jerry appreciates that. Anyway, doing that. And those are our grandchildren, Soren and Greta, in Boise, Idaho, where we get a chance to visit them. But thank you, Leslie, for your support throughout all this stuff. And I don't know if we have any moments for questions or answers, wherever. What happened to them? I'm going the wrong direction. There it is. All right. No promise on the answer.
We do have time for some questions. Raise your hand and you will be given a microphone to ask your question.
Oh, yeah.
I think everybody could have probably heard me anyway, but you mentioned that iron oxidation occurs before DBP formation, NOM oxidation occurs?
We have to set the context, but yes, I said it in the...
Right, yeah.
Anyway,
Can you tell me whether bromide was present in the water? Does bromide go before iron, or does iron go before bromide? Because in Texas, we have a lot of water with bromide in it.
Yeah. So the real answer to that question, anybody who's taught kinetics realizes that dCdt is a function of a constant intrinsic to the reaction and the concentration of the reactants. All right? So what we're interested in is the dCdt part. So it's not just about the rate constant. So iron is probably going to be a lot more abundant than bromide. That gains it to be, but maybe not. NOM is quite abundant, so it's good that K is pretty slow on that one for the free chlorine. Probably, do you know the answer? I can't. Bromide reaction's really fast. I think the bromide's going to go. Yeah, I think bromide is going to beat iron. Yeah, it's annoying that I do have a slide from Dave which has the half-life and calculations. And this pH and all the other factors. But I think bromide it's so fast. Yeah, good question. That's a good question. Yeah, I left out a few reactants. Which could be in there. Some other question, anybody?
I may have, sorry, my bad, thanks. I may have misread this plot, but I think there was a graph where you showed the secondary contactor that showed the distribution of manganese, and there was an increase after the oxidant stage where it increased colloidal concentration. There was a plot. Would you be able to show that and see, is that correct?
So if, let's see.
Yeah,
I mean, I can, we gotta go, I just went past it.
I think that was it.
Right there. So which one? Which bar on this?
It seemed like there was an increase going from raw water to dual media influent colloidal concentrations.
Yeah, I'll explain that.
Thank you.
Yeah. That's manganese associated with the iron colloids. Iron precipitated. Or it may be a little bit of manganese got precipitated, but unlikely. And if it did, it would have been catalyzed by the surface it was on, not in solution. So it's probably associated with that. Like when we do this separation and I measure iron and manganese, right? I can't tell if the particle or the colloid is what it's made of in this particular way. Yeah, good catch on that. Yeah. There's some weird stuff that happens with permanganate. I got to say that. I want to get back to this plant. Sometimes it appears that permanganate comes through, or manganese comes through dissolved greater than in the raw water, but really measures as dissolved. And I don't know that if it's really Mn7 permanganate, because the water's not pink. All right, so there's some interesting stuff there, but all with the colloids and things. Fortunately, the second stage takes care of it. But yeah. No, the contactor is quite robust. I will say the colloids on the surface of the media in the contactor are fragile. That plant, when it ran for the first 2 years, we did every backwash. We brought sample back to the lab. We measured how much manganese came off, and it was pretty much 100% removal. We knew what we took out in the contactor, and all of it backwashed off. Plus, we measure the concentration of manganese on the media. We've done it now every few years for the utility. It's really painful. One of those really hard to get to things. So if you ever go out and say to someone, can I get a sample of your media? It is not a simple question to anybody who runs a water treatment plant. That's a hard place to go. But it didn't accumulate. So there was a question that you had raised in the middle. Wait a second. Or can you get her? Could be.
I'm scared. I'm not used to using a microphone. But my question was, what causes the buildup of different... You said that, you're talking about the manganese and iron. You said that sometimes there's a buildup of those metals in fire hydrants. And I was wondering what causes that.
Oh, I'll explain what I was getting at. So in distribution systems that have reduced iron or manganese in the raw water, and the approach to treatment is to add, in that particular case I was discussing, a sequestrant, a chemical that's meant to bind with the Mn2 or Fe2 and magically prevent free chlorine from oxidizing it, okay? I'm sorry, a little cynical about that. Prevent free chlorine from oxidizing it, okay? So that's supposed to happen, but it often doesn't happen. And so in the course of hours or a half a day or 2 days, you go out to a person's home on the street and you take a measurement and you find out the manganese and iron, which if it was sequestered and stayed dissolved, should be exactly the same as leaving the treatment plant. There's like 20% of it that is, 80% is gone. It's somewhere. You go to the distribution system and say you want to flush it, so you open a fire hydrant to flush it, and that thing flowing out is just black, orange particles in the water. They all deposit in the distribution system. So slowly going along, free chlorine and Mn2 plus, eventually you'll oxidize it. Iron, iron is more aggregation because it's oxidized. At least every time we've added a sequestrant and then free chlorinated it, it's colloidal iron. It's not dissolved. It just doesn't stay there. So that's it. It was that it was precipitating in the distribution system and then can be flushed out.
Okay, I just want to make sure I'm understanding this correctly.
Yeah.
The chlorine is one of the things we put in the water to disinfect it.
Yes.
The water naturally has some minerals in it, like iron and manganese.
Right in the source, yep.
And that's from even the soil. It naturally has those minerals in it.
Yeah. Much of our crust.
The chlorine that we put in the water to disinfect it reacts with the iron and reacts with the manganese and causes it to
oxidize, and it turns out when it oxidizes to Mn4 or Fe3, the chemistry of that is that they form precipitates. They're very insoluble. Solubility of iron 3 at pH 6 is 10 to the minus 10th molar or something like that, some absurd number. Anyway, it's 4 orders of magnitude less than aluminum.
So what?
So it's Yeah, so it oxidizes and makes particles. Yeah.
Okay, and before it oxidizes, what's it made out of?
Which?
Either, like, what's the
It's a
formula?
dissolved ion in solution.
Okay, and
It's clear. You can't see it. Yeah, if I hold you a glass with 1 milligram per liter of Mn2 plus in it, it's clear as day.
so the only difference is that it solidifies,
Yeah, it changes form and becomes a particle.
but it's still the same particle.
It's the same element, a different part. It
Okay.
wasn't a particle, and now it is. Yeah. All right. Yeah. Yeah, and then it goes out. Yeah. All right.
Okay, thank you.
Bob, did you have a question? I know people are needing to go. Are we good? All right. Yeah. Thank you. Thank you for listening. Appreciate it. Thank you very much.